Hello everyone. Good evening. Here we shall some more KCET previous year questions on the chapter Thermodynamics. So, any doubts if you have in any steps, then please write that in the comments section. We shall obviously clarify them in the subsequent videos, and also in any other chapter of physics. If you have more difficulty, then also mention the name of that chapter in the comments section, so that we can give more clarity on it and solve more and more questions on that chapter. Also, some important homework questions will be uploaded in the Sapience Education application. So please install our Sapience Education application, whose link has been provided in the description. So here it has been told that a number of Carnot engines are operated at identical cold reservoir temperatures TL. So here there is a cold reservoir, and however their hot reservoir temperatures are kept different. uh, a, a graph of the efficiency of the engines versus hot reservoir temperatures is plotted. The correct graphical representation is, so here we have the hot reservoir. So the hot reservoir is kept at temperature TH, the cold reservoir is kept at temperature TL. Now they are being connected, and so this is the Carnot's engine. So here the work done work done by the engine, which is the output energy, by the energy input, which is the heat which is being supplied, that is called as the efficiency of the Carnot's engine, and that is given as 1 minus TL by TH, where TL is the temperature of the cold reservoir and TH is the temperature of the hot reservoir. So here we have been told that TL is constant, means TL is same for all the Carnot engines. TL is the same for all the Carnot engine, but the hot reservoir temperatures are not same. Means TH is variable here, and so eta will also change. The efficiency eta will also change. So here we have to plot a graph of eta versus TH. Now, as you can see that if we keep so at TH equals to TL, the efficiency will become 1 minus 1, that is 0. And as the as limit TH tends to infinity, means when the value of the cold so, the temperature of the reservoir is very high, it means if TH is much higher than TL, then we can say that limit TH tends to infinity. So then eta will tend to 0. No, eta will tend to 1. Means eta will tend to 1 minus 0, that is 1. So it means the graph will be somewhat like this. The efficiency eta versus TH, the graph will start from here, and it will be like this. So at t tends to infinity, the efficiency value will be 1, and at th equals to TL, the efficiency will be 0. So the graph will be like this. So it means option B is the correct answer. Here it is told that heat cannot itself flow from a body at lower temperature to a body at higher temperature. This statement corresponds to. Since why this process is not a spontaneous pro process. It is not a spontaneous process. So which process will be spontaneous and which process will be non-spontaneous? has been explained only in the second law of thermodynamics. Only in the second law of thermodynamics, the um, the spontaneity of a process has been explained. The spontaneity has been explained. Simply, it has been told in the second law of thermodynamics that a process will be spontaneous only if the change in entropy of the universe is greater than zero. It means though only those processes will be spontaneous for which the entropy of the universe increases. Now, entropy of the universe, I can say it is the sum of the change in entropy of the system plus the change in entropy of the surrounding. So, if the sum of these two is greater than zero, then only the the process will be spontaneous. Process is spontaneous. So, hence, a heat the heat e- energy cannot flow from a body at lower temperature to a body at higher temperature. This statement corresponds to the second law of thermodynamics. So option B is the correct answer. Here it has been told ideal gas heat engine operates in a Carnot cycle in between the temperatures to 227 degree Celsius, which is the temperature at the hot reservoir, and the temperature of the cold reservoir, that is TC, which is 127 degree Celsius. And it is told that it absorbs a heat energy of 6 into 10 power 4 joule, then the amount of heat that will be converted into work that we have to find. So as we know, work done by heat which is supplied, that is equal to the efficiency of the Carnot's engine, and that is equals to 1 minus Tc by Th. 1 minus the temperature of the cold reservoir by the temperature of the hot reservoir. And these temperatures should be taken in Kelvin. So therefore, here Tc will be 127 plus 273, 127 plus 273, so that is 400 Kelvin. And Th, the temperature of the hot reservoir, is 273 plus 227, that is equal to 500 Kelvin. So therefore, the work done will be equal to the efficiency, which is 1 minus Tc by Th, 1 minus Tc by Th into the amount of heat which is being supplied. So that will be equal to 1 minus 400 by 500 into Q, that is 6 into 10 power 4 joule. So this will be 1 minus 4 by 5, that is 1 by 5, 1 by 5 into 6 into 10 power 4 joule. So this will be equal to 1.2, 1.2 into 10 power 4 joule. So option 4 is the correct answer. So 1.2 into 10 power 4 joule of work uh, will be obtained from this Carnot's engine if the heat supplied is 6 into 10 power 4 joule. Then here it is told blowing air with open mouth is an example of. So when air is blown from the mouth, when air is blown from the mouth, then the external pressure is the atmospheric pressure. Atmospheric pressure is acting in the surrounding, and when the air is blown, then also the pressure of the air will be same as the atmospheric pressure only. So it means here in this process, the pressure of the air is remaining constant. Here, the pressure of the gas, which is the air, it remains constant, and which is also equal to the atmospheric pressure of the surrounding. is equal to the atmospheric pressure of the surrounding. So it means since the pressure is constant, so it is an isobaric process. So it is an isobaric process. So option 3 is the correct answer. Then here it is told an ideal monoatomic gas is taken around the cycle A, B, C, D, A. So it starts from the point A and then it returns back to A as shown in the PV diagram. The work done during the cycle is given by. So we know that work done in the cycle equals to area under the PV diagram. So area under the PV curve, we can say. So here so it is forming a rectangle. So yeah, so it will be simply length into breadth. Simply it will be the length of AD, which is same as the length of BC also, and AB length is also same as the length of CD. So AB means, sorry, is AD is the length and the breadth is AB. So AD into AB. Now the length AD is, here we can see, so it starts from the point A. From here to here, the length is 2V minus V, which is V. And from A to B, this length is 2P minus P, which is P. So the area is PV. So the area is PV only. So the work done in the cycle is PV. So option 2 is the correct answer. Then here it is told oxygen is 16 times heavier than hydrogen. Equal volumes of hydrogen and oxygen are mixed, then the ratio of speed of sound in the mixture to that of hydrogen is. So here oxygen, we know that it is 16 times heavier than hydrogen only, since the atomic mass of hydrogen we know that is equal to 1U and the atomic mass of oxygen is 16U. Now equal volumes of hydrogen and oxygen are being mixed. So if we take ideal gas, then the speed of sound in a gas, that is given as root over gamma p by rho, where gamma is the ratio of the specific heat Cp and Cv, and P is the pressure of the gas, and rho is the density of the gas. Or it is also written as root over gamma RT by M also. Since we know that PV equals to nRT, and N can be written as mass by molar mass into RT. So I can say Pm equals to M by V into RT. Now M by V is mass by volume, which is called the density. So I can say Pm equals to rho RT. So I can say P by rho is also same as RT by M. So gamma P by rho is also same as gamma RT by M. And gamma is the ratio of the specific heat Cp by Cv, which is also equal to 1 plus 2 by F, where F is the number of degrees of freedom of the ideal gas. Number of degrees of freedom, the ideal gas. So if it is a monoatomic gas, F is equal to 3, and if it is a diatomic gas, if it is monoatomic gas, then it is 3, and if it is a diatomic gas, then it is 5. So now, so as we know, hydrogen and oxygen both are diatomic gases only. So the value of gamma for hydrogen is same as the gamma for oxygen, which will be equals to 1 plus 2 by 5, which is equal to 7 by 5, since both are diatomic gases. And so here, the pr pressure will be the same only. Okay, so as we know that molar mass of hydrogen, that will be 2 gram, and the molar mass of oxygen, that will be 32 gram. And if same volume of them are being mixed, then molar mass of the average molar mass of the mixture, if you have to find, so that will be the molar mass of oxygen into the volume of oxygen into, plus the molar mass of hydrogen into the volume of hydrogen divided by the total volume of oxygen and hydrogen. So therefore here it is told same equal volumes of hydrogen and oxygen are being mixed. So therefore we can say that therefore therefore the molar mass of the mixture, that will be equal to molar mass of oxygen, which is 16 gram, into, let's say, V. So here it is told that the volume of oxygen is same as the volume of hydrogen, which is V, let's say, since they are same, it has been told. So it means so it will be 16 gram into V plus 2 gram into V by 2V. So that will be equal to 6. Okay, so it will be 16 plus, no, sorry, this will be 32, sorry, not 16, this is 32 gram, 32 gram, 32. Okay, so it will be 34V by 2V, this much grams. So this will be 17 gram. So the molar mass of the mixture is 17 gram. So now, therefore, and the gamma of the mixture also will be 7 by 5 only, since both are diatomic gases, since both hydrogen and oxygen are diatomic gases. Atomic gases. So now, therefore, the velocity of sound in the mixture, the velocity of sound in the mixture, that will be equal to gamma mixture into RT by molar mass of the mixture. Now that will be equal to 7 by 5 RT by into 17. Suppose here we assume that the temperature is remaining the same. The temperature is constant. So now, therefore, and the velocity of sound in hydrogen, that will be equal to the gamma of hydrogen into RT by molar mass of hydrogen. So this will be also 7 by 5 into RT by 2. So now, therefore, we have to find the ratio of the speed of sound in the mixture to that of hydrogen. So the velocity of sound in mixture by velocity of hydrogen. So that will be equal to root over 7 RT by 17 into 5 divided by root over 7 RT divided by 5 into 2. So therefore this RT will cancel, 5 also will get cancelled, 7 also will get cancelled. So this is coming root over 1 by 17 divided by root over 1 by 2. So this will be equal to root over 2 by 17. Root over 2 by 17. So therefore option 4 is the correct answer. Now here it is told the PV diagram of a Carnot's engine is shown below. The engine uses 1 mole of an ideal gas as a working substance. From the graph, the area enclosed by the PV diagram is. So we know that area enclosed, area enclosed by the PV diagram, area enclosed by the PV diagram, that is equal to work done. It is equal to the work done, and that is also equal to the energy output. We can also say it is the output energy. So now in a Carnot's cycle, we know, so in a Carnot's engine, In a Carnot's engine, here the energy output, which is the work done, divided by the supplied, heat supplied, which is, it means it is the energy output by energy input, that is called as the efficiency of the Carnot's engine. Efficiency of the Carnot's engine, and that is equal to 1 minus the, the temperature of the cold reservoir by the temperature of the hot reservoir. So therefore, the work done, that can be also found out like this, which is equal to the efficiency times the heat that is supplied to the gas. Q. Q is the Q I am saying, where Q is the heat supplied to the gas. Supplied. So now here we can see in the graph, since it is a Carnot's engine, now the region from C to D is called isothermal compression. Here we have isothermal compression, and from D to A, in the region D to DA, here we have adiabatic compression, adiabatic compression, and then from A to B we have isothermal expansion. Since here the volume is increasing, isothermal expansion, and the region from B to C we have adiabatic expansion. Adiabatic expansion. So now it means at the point C, we can find out how much is the temperature at the point C. Since it is an ideal gas, so we can use PV equals to nRT. So the temperature at the point C, okay, so here we, okay, here there is no heat change. So here, okay, the temperature at the point C will be the temperature of the cold reservoir, and the temperature of the point A will be the temperature of the hot reservoir. So the temperature at point C, we can write it as PC into VC by N R into T. No, sorry, PV by NR. PV by NR. PC VC by NR. Similarly, so which will be the temperature of the cold reservoir? Temperature of the cold reservoir, and the temperature of the hot reservoir will be the temperature at the point A, which is equal to we can say PAVA by NR. PA, it means the pressure at the point A, and VA is the volume at the point A. And similarly, PC is the pressure at the point C, and VC is the volume at the point C. So now, therefore here, therefore now here in the graph, we can see that PC, which is the pressure at the point C, is 400 kilopascal. So it is 4 into 10 power 5 Newton per meter square, or you can say Pascal. Similarly, the volume at the point C is 6.25 centimeter cube. 6.25 centimeter cube, which you can also say in the SI unit, it is 6.25 into 10 power minus 6 meter cube. So therefore, the temperature at the point C, and here it is told that 1 mole of an ideal gas is used as a working substance. Therefore, the number of moles is equal to 1 here. N is equal to 1. 1 mole is used. 1 mole of ideal gas is used here. 1 mole of ideal gas is used. So the temperature at the point C, which is the temperature of the cold reservoir, and TH, which is the temperature at point A, it is the temperature of the hot reservoir. This TH is the temperature of hot reservoir here. So now the temperature of the cold reservoir will be equal to Pc into Vc by Nr. Now n is equal to 1. So therefore we can say it will be 4 into 10 power 5 into 6.25 into 10 power minus 6 divided by 1 into R. And this will come in Kelvin, obviously. So this will be equal to yeah, so 0.4 into 6.25 divided by R in Kelvin. Now, so this will be equal to 2.5 by R Kelvin. We are not inserting the value of R here since why when we find the efficiency and we find the ratio of TC and TH, then this R will get cancelled. So we are not placing the value of R here. So simply we have found TC in terms of R only, where R is the ideal gas constant. R is called ideal gas constant. So we are not using the value of this R here since it will get cancelled. It will get cancelled when we find the efficiency of the Carnot's heat engine. And similarly, we can find the temperature of the hot reservoir, which is TH. Since the pressure at the point A, that is given as 1600, 1600 kilo Pascal, which I can write it is 1.6 into 10 power 1.6 into 10 power 6 Pascal or Newton per meter square. And similarly, volume at the point A, that is equal to 2.5 centimeter cube, or I can say it is 2.5 into 10 power minus 6 meter cube. Therefore, the temperature of the hot reservoir, that is equal to PAVA by NR, which will be equal to PA is 1.6 into 10 power 6 into 2.5 into 10 power minus 6 divided by 1 into R, this much in Kelvin. So therefore, if we solve it, then this will cancel. So 1.6 into 2.5. So this will come as, yeah, this will come 4 by R. 4 by R Kelvin. Therefore, so we can say the efficiency of the Carnot's engine will be 1 minus Tc by Th, which is 1 minus temperature of cold reservoir by temperature of hot reservoir, which is 1 minus Tc, which is 2.5 by R, divided by temperature of hot reservoir, which is 4 by R. So R and R will cancel. So this will come 1 minus 2.5 by 4. So this will be 4 minus 2.5 by 4, which is equal to 1.5 by 4. Therefore, the work done we have to find, since here it is asked to find um, the area enclosed in the PV diagram. Work done is same as the area under PV diagram, and that will be equal to the heat which is supplied times the efficiency. Now the heat supplied has been told that it is equal to 8,000 joule. So it is 8,000 joule into efficiency, which is 1.5 by 4. So this will be 2,000 into 1.5, which is 3,000 joule. So it means the option A is the correct answer. So hope all of you have understood the solutions of these questions on the chapter Thermodynamics on the previous year KCET exams. Still any doubts if you have, then please write that in the comments. And please install our Sapience Education application also. since we shall upload some important questions based on the previous year KCT exam, which shall be obviously helpful for your exam. So thank you everyone. Bye.